want to give you a little bit of bonus material at this point. This is day 3, and on your homework outlines, this is labeled as extra. But I want to give you just a couple of minutes on this because it's an important concept that reinforces what we did in day 1 and day 2, and adds a little bit of credibility to that C value at the end. So here's the idea. We're going to use the idea of an initial condition under the guise of a family of antiderivatives with that whole plus C idea to find a specific solution for an antiderivative. And we're going to apply specific solutions to the context of motion really briefly. This will be covered a little bit more formally later on in this chapter and then again in chapter 6, but I want to give you a little bit of an idea here. Here's an example. I'll actually just go through one of these. Well, let's talk about it briefly. If we're given a function, f of x equals 3x squared, we know that through that antiderivative from yesterday, it produced f of x equals x cubed plus c, and that's power rule, or just kind of a simple recognition that a quadratic becomes a cubic when you're doing an antiderivative process. Now, all of these are x cubed. If we look at that on a graph, it's x cubed, or you could move that up, or you could move that down. So there's a whole family of antiderivatives. Now, if we know something about a specific antiderivative, in this case, it gives us an initial condition of f of 1 is 4. We can find the particular solution. So we can find the specific antiderivative that's in the family of antiderivatives that we're looking for. So we know that it passes through 1, 4. We're going to use that idea that that xy ordered pair is on the function, and we're going to go ahead and set f of 1 equal to 1 cubed plus c. And we are told that f of 1 is equal to 4, so we should be able to see here that's 1 plus c, so c is equal to 3. So the specific antiderivative we were looking for here was f of x equals x cubed plus 3. Okay? It allows us to go from general to a little bit more specific. So we'll do one more, and then we'll get to a position problem. Okay? We've got a function f. We're finding the antiderivative that satisfies the given condition. So we're asked to find an antiderivative, so we'll do that part first. This is not a power rule. It's secant squared. This is one you have to recognize. Its antiderivative is tan t, because we're dealing with the variable t, plus a constant of integration. The initial condition, then, we will substitute. Capital F of pi over 4 is equal to tan of pi over 4 plus c. You should know from memorizing unit circle or otherwise that tan pi over 4 is 1. So this would be 1 plus c, and we're told that that's equal to 1, so c is 0. The particular antiderivative we were looking for here then was tan t plus 0. Plus 0 does not need to be written, so you could just leave your answer as f of t plus tan t. Okay? I'm going to skip this one for now, for the time being. Key here, if you want to go through it, it's in your notes. The key here is to simplify, because you have a single term denominator. If you're going to go ahead and do that problem, I would write it as 4x to the 1/2 over x squared, simplify the exponents, 6x to the negative 1/2, 6x to the negative 1/2 over x, no, that's right, over x squared. And then I would do it that way. If you want to talk to me or your teacher on the actual solution for that, we'd love to talk to you about it. So here's an initial value problem idea. Just a little bit of a reminder that S of t typically applies to position. V of t is the derivative of S of t. And A of t, that's V is for velocity, and A is for acceleration. And A of t is S double prime of t, which is also V prime of t. So that derivative relationship is really important. And when we're going backwards, most of the time you're going to be given acceleration and asked to go back to position, or given velocity and go back to position, whereas before you were doing them the other direction. So we'll do one example and call it a day. It gives us the acceleration is 4. Key here is acceleration is constant. We can't assume that's always true, but on Earth, typically here it is. Acceleration is not typically 4, but acceleration due to gravity is a little bit different. But we'll go ahead and use this premise anyway. So we're told that A of t is 4, and we're told 2 initial conditions. And I know they're initial conditions because 0 is the time value given. Anytime you're given a 0, that's an initial condition. So the constant A of t equals 4, we'll go ahead and integrate that. Antiderivative will give us a velocity function, and v of t is equal to 4t plus the constant of integration. We're given an initial condition involving velocity, so we'll go ahead and substitute that value in. V of 0, we're told, actually we're not told this, but we can substitute 0 for t, and then we're told that that value is -3. So we should be able to conclude that since that portion is 0, that c is -3, and the velocity function in terms of time, with respect to time I should say, is 4t minus 3. We can then go back to position. If we then take that antiderivative process again, we'll get back to position. S of t will be equal to 4t squared over 2, which is 2t squared, minus 3t plus a constant of integration. We'll use that initial condition. S of 0 is equal to 2 times 0 minus 3 times 0 plus c, and that we're told that that's equal to 2 from up here. So the c value is 2. Our position function at any time then is 2t squared minus 3t plus 2. And what we've done is we have found a specific solution out of that family of antiderivatives. And the only reason we could do it is because we were given initial conditions in the process. Here's your day 3. These problems are extra. I encourage you to try some if you've got time. They're good antiderivative practice, and then a nice little application as well. Have a great weekend.